All right, so we're gonna finish introduction of chapter 8 today, and that will leave us open for review next Friday on the 31st. Today we have scheduled a lab Boyle's Law. If nobody shows up, then I'll think of something. But in the meantime, let's get chapter 8. Let's get chapter 8 going. Remember, chapter 7 was on gases, liquids, and solids. So we finished off with, I think, the gas laws. That's why Boyle's Law is today, because we got it. We were introduced to it last week. This week we're going to study solutions, and next week after the review we're going to have a lab molar mass by freezing point depression. So we're moving that one. That one is next week because we're going to cover that topic today. Okay. I see. Okay. Let's see. Shared, and let me move some things around so I can see what I'm doing. All right. So these are the topics we're going to cover today. We're going to learn how characteristics of solutions. We're going to learn how to express concentrations in various forms. We're going to learn about solubilities. Some compounds are soluble in water and some are not. And we're going to learn how to tell whether or not the products of a chemical reaction will be soluble. Then we're going to talk about dilution, right? That's an interesting topic. And then some colligative properties. And I'll define what colligative means when we get there. All right. I think we've introduced this concept early on in the semester when we were talking about mixtures. A mixture that is homogeneous throughout is also called a solution. So that means that it does not have to be a solid dissolved in a liquid, like salt in water or sugar in water. That's only one type of solution. There are a whole host of types of solution as long as the mixture is homogeneous. So we could have a solid and a liquid that we normally think of solutions. You can have a liquid and a liquid, right? Alcoholic beverages are like that. You can have a gas and a liquid. That's why when you crack the top on your bottle of pop, it fizzes, because there is gas dissolved in the liquid. You can have a solution of 2 or more gases. We breathe that every day. Nitrogen primarily, 78% nitrogen, 21% oxygen, and the rest minor components. That's a solution. And remember, anytime you put 2 or more gases together, you always get a solution. You can have a solid solution like brass, which we also call an alloy. Any alloy, metal alloy, is a solution. So when we describe a solution, we describe it in terms of what's the major component. The major component is the solvent. And there can only be one. Only one solvent. But you can have many solutes. Those are the minor components. So if I want to make sugar water for my hummingbirds, I'll boil water, because sugar goes into solution faster if it's hot, if the water is hot. The water then is the solvent. And the sugar that I add to it is the solute. Now, interestingly enough, you can keep adding sugar to the water, the solution of water and sugar. You can keep adding more sugar to it, and eventually you'll get to the point where there's more solute in it than there is solvent. But since we started off with water as the solvent, it stays that way, even if the solute becomes a major component, just to keep things simple. All right, so here's an example of some colored crystals. We don't know what they are, mixed in water. We know that this is a solution because we can see through it. Right? We don't see any particles suspended moving around. Now, sometimes, we're going to talk about this later, sometimes you get things that particles are so small, they remain suspended. And it looks like a solution to the naked eye, but it's not. And we have a way to tell the difference between those two. Let me check my hard copy. Okay, just checking. I don't want to steal my own thunder. So later on, I have a slide that'll show you an example of how you tell the difference between a true solution and a suspension that does not settle. Most suspensions will settle, but there's a class of suspension where the particles are so small that the kinetic energy of the solvent is sufficient to keep the solute, well, we can't call it a solute, but keep the suspended particles from settling. All right, more about that later. All right, these are general properties of solution. Obviously, you have two or more components. One of them has to be the solvent, and the rest can be solutes. So you can have, the sky is the limit, any number of solutes, but only one solvent. They can have variable composition, that is, the percent of solute in the solution can vary, right? Because there's no chemical reaction there. It just depends on how much you put in as to what the concentration is. And then, of course, there's a caveat there. Most solutions, you can reach a point where the solute, the maximum amount of solute that can be dissolved, you can't go any higher. At that point, we say the solution is saturated. Anything you add after that will just settle out. There's no room for it in the solute. In the solvent. The properties of a solution can change as the ratio changes. As you steadily increase the solute, the physical properties can change. For instance, if we add more solute, let's say, you're going to make a starch solution, so you can, dump it in your sauce and thicken it up. Well, the more starch you put in there, within limits, of course, the thicker it gets. So the viscosity of the liquid increases as we add more starch. That's just one example. Another example we'll talk about later is, as you add more solute, the freezing point of the solution goes down. You have to get it colder before it will solidify. That's one of those colligative properties. The solutes can be molecular, right? They can be molecules like sugar molecules. They can be ions like sodium and chloride. If you dissolve table salt in water, then they break apart into individual ions. Or they can be separate atoms. You can dissolve gaseous atoms like hydrogen. You can put it in solution, and it's, well, that's diatomic. That's not a good example. Oh, I'll paint myself into a corner here. The solution, oh, you could have metal alloys. There you go. Like copper and nickel will make brass, and they're individual atoms, metal atoms in that solution. The solutes remain, by definition, uniformly, homogeneously distributed in the solution, and they will not settle. And because there's no chemical change that's taken place, no change in identity of either the solutes or the solvent, then they can be separated from one another by physical means. Right? Example, if you have salt water, say you put sodium chloride in water, that we call that aqueous solution. All you have to do is evaporate the water and you get your sodium chloride back. That's a physical process that will retrieve components of the solution. So if we have 80 milliliters of water and 20 milliliters of alcohol in a solution, which one is the solvent and which one is the solute? Well, by definition, water is the solvent and alcohol is the solute. Okay. By the way, that would be 40 proof alcohol. All right. So I mentioned earlier that there's a limit to how much solute can be dissolved in the solvent. That term is called solubility. The solubility is an expression of the maximum amount of solute that will dissolve in a given amount of solvent under a given set of conditions. For example, you can put so much sugar into solution at room temperature. If you heat it up, you can put more in. You can get more sugar into solution. Then if you let it cool and you give it some place to crystallize, like you drop a crystal of sugar, table sugar in there, gives it something to hang on to. Then as it cools, the excess sugar will collect around that crystal and it'll grow. That's how they make rock candy. They grow the crystals. Okay, that term is solubility. And we have various ways of expressing that solubility. It is an intensive property. In other words, the solubility is the same for a given temperature. And if there's gases involved, then at a given pressure. But if those conditions don't change, then the solubility is the same no matter how much of it you have. Solubility, the maximum amount of solute that can be dissolved in a solvent, usually for solids, they become more soluble as the temperature increases. And this is in particular aqueous solutions, which is our primary focus in this class. However, as you increase the temperature of the solvent, the solubility of a gas decreases. That's characteristic. So, for example, if you fill your pot up with water and you put it on the stove to boil, as it starts heating, the first thing you'll see is on the bottom of the pan, you'll start to see little bubbles. Those are not water vapor. Those are dissolved gases in the water. So you already have a solution of dissolved gases, usually nitrogen and oxygen from the air, in the water, and when you heat it up, it becomes less soluble, so the gases come out of solution as little bubbles. That's the first step. Then once all of those disappear, pretty soon after, you'll start boiling the water and producing water vapor. Okay, so here we have an example, a table showing solubilities of various compounds in water at 3 different temperatures. So at 0 degrees, or the freezing point of water, assuming it's still liquid, of course, the solubility of lead-2 bromide is very, very low, while the solubility of cesium chloride is very high. So it varies, solubility varies with the compound. And as you increase the temperature, the lead-2 bromide becomes more soluble. And silver sulfate, yes, becomes more soluble. Copper sulfate, more soluble. Sodium chloride, more soluble. Not much, but a little more soluble. Silver nitrate becomes more soluble, and cesium chloride becomes more soluble. So on those particular compounds, increasing the temperature increases solubility. And notice the solubility is expressed in terms of grams of solute per 100 grams of water. That's typically the way you will see it expressed in reference manuals. Come on. There we go. There's an exception to the rule. Some compounds become less soluble as the temperature increases. The example I give there is calcium acetate. Unfortunately, there's no way to predict. You just have, this is empirical information. You just have to run the experiment and determine that calcium acetate is less soluble as the temperature increases. And if you're really interested in that particular compound, you'll probably measure the solubility at different temperatures and draw a graph so that you can predict the solubility in the future with temperature. What effect does pressure have on solubility? Well, if the solute, let's see, pressure effect. If the solute is a solid or a liquid, no effect. But if it's a gas, you have a substantial effect of solubility of the gas with pressure over the solution. So if you have the liquid, the solution is confined in a sealed container, then the gas is up here and the solution is down here. If you increase the pressure up here by adding more gas molecules, more moles of gas, then you will get an increase in solubility, an increase of solution dissolved, the gas dissolved in the solution. Now, I'll say it now because it's stream of consciousness. If you increase the pressure here by adding an inert gas like helium, right? The helium, as you add it, may become more soluble in the solution, but the other gas that's in there with it will not become more soluble. In other words, the pressure is dependent upon how many moles of the gas that you add to increase the pressure. Or if you decrease the volume, right, that will increase the pressure. All right, so here's an expression of the effect that pressure has on the solubility of a gas. This is called Henry's law. So Henry's law is very simple, right? As most of these types are. Concentration of the gas in solution is proportional to the pressure. And then H is Henry's constant. Henry's constant is constant for a particular gas at a given temperature, right? So it's constant, yes, but it's not constant because it changes with the gas and it changes with the temperature. But once you know this relationship, we can say something like this. Let's solve it for the constant. Right? Like we did with our earlier gas laws. Right? If this is constant, then the concentration will increase as the pressure increases. Right? This is a direct proportionality. So if this is your concentration at one pressure, this is your concentration at a second pressure, then all you have to do is change the volume here, squeeze it, get a different pressure, and you can predict the concentration of the gas in the solution. That's Henry's law. I believe that was his last name. Okay, here's a saturated solution. Saturated solution is one in which no more solute can be placed into the solution. It sits there as a solid. Okay, that's known as a saturated solution at a given temperature for a solid and a liquid. For a gas, we also have to take into account the pressure. But usually, I'm trying to think, gases, gases have a saturation concentration, but it's not as easy to determine because you can put a lot of gas in solution if you increase the pressure high enough. Just ask any diver, right? If you go down to, say, you dive to say 100 feet or 150 feet, then the pressure on your body is going to drive oxygen and nitrogen from the air that you're breathing into your tissues because the pressure is increased on your body. So if you try to come up too fast, as the pressure decreases, that gas comes out of solution. The oxygen's not the real problem. The real problem is nitrogen. Nitrogen will come out wherever it's convenient. And one of the places that it comes out is in your joints. And it causes excruciating pain, they say. And a person that's in that kind of pain will bend over. And that's why they call it the bends. So what divers will do is if they're down at a certain depth for a given amount of time, and they have charts that tell them how long they can stay there. And if they stay there over a certain amount of time, then as they come up, they have to stop. They have to check the depth gauge and stop at a certain depth and wait for, I don't know, 20 minutes or so. It depends. And then they can come up to the next depth and wait. Give the dissolved nitrogen time to come out of the tissues, and you can expel it in your breath. If you come up too fast, then you've got to be put in a compression chamber very quickly. And service boats that have divers that are going to work at depths of 100 meters, 200 meters, they actually have to work like workers on divers around oil platforms. They have to be maintained underwater, so they have specialist divers that do that. If they're down there for a certain amount of time and they're at a certain depth, then and they have to come up quickly, like they're injured or they're attacked by a shark or a barracuda or some other animal, then they have to come up quickly. Then the boat or the oil rig has a compression chamber available. And they go right in the compression chamber, pressure is increased, and then it's gradually decreased over time. Otherwise, it could kill you. The bends can be fatal. Okay, what's a supersaturated solution? Well, if we've got a solution that's already got as much solute as it'll hold, right, how can you get more in there? Well, as it turns out, this is an unstable condition. And for example, one way to supersaturate a solution is to heat it up, make it hotter for most compounds, and put an excess amount. You know how much mass of solute will go into 100 grams of solvent, say, let's just say water. So you heat it up, and that means that all of it will go into solution. And then you allow it undisturbed to gradually cool. And very often what you'll get is a supersaturated solution at room temperature. Now, all you have to do is disturb that solution, and the excess solute will come out of solution very quickly. For instance, you can stir the solution, or you can scratch the glass on the inside of the beaker, or you can add a solid crystal of the solute in there, and it gives it something to collect around, and it will come out of solution like that. That's a supersaturated solution. Unsaturated solution is simply one that doesn't have all the solute that it can carry. You can put more solute in an unsaturated solution. Other qualitative descriptors. A concentrated solution is one that has a large portion of the solute in the solvent at relative to its saturation point. So if you can put 5 grams in 100 milliliters of water, then 4 grams of the solute would be considered concentrated. But a dilute solution would be one in, say, you would have a 1/10 of a gram. So it'd be much, much less. See, those are relative terms. You want to join? Sign in.
Only one here.
Yeah, well, I've got 2 on Zoom, but they're going to miss the lab. One of them is bona fide sick. The other one, I think, is having car trouble. So I'll pause for a second. I think I've got I got a graded paper for you. This is determining density. All right, so we're into chapter 8. I don't know how many slides we've viewed so far. Maybe 12, 13, 14, 16, something like that. Okay. So one way to prepare a concentrated solution from a dilute solution is just find some way to remove the solvent. If you have the same amount of solute, but you decrease the amount of solvent, then it concentrates. And this slide shows you that you can tell the indicator here is a change in color. So the color is light blue on the right and dark blue on the left because we've allowed water to evaporate from it. Most of our discussion will be concerning aqueous solutions. That is, those in which the solvent is water. Non-aqueous solutions do exist, and we mentioned a few of them in the beginning. And they're important for special applications. Non-aqueous solutions are extremely important for organic chemists. The reason being that if your reactants are in aqueous solution, the water itself can become a reactant, and you can get undesirable side reactions with the water. In fact, you can get reactions that will completely negate the one that you want. So many organic reactions are conducted in non-aqueous solutions. Okay, how does temperature and pressure affect the solubility of gas in water? Well, increased temperature decreases the solubility, pressure increases the solubility. Okay, now we've talked about generalities and in terms of qualitative descriptors and one law for making a solution. Now we're going to try to look at, I guess you could call this a theory. This is a way of, we're trying to understand what happens when a solute goes into solution, when it dissolves in a solid. And it can be divided into 3 steps. Now, of course, these 3 steps are designed to help us understand it. In fact, they occur simultaneously. So one thing that has to be done, if you've got a, let's see, let's remove that. If you've got a first step, let's do it that way. First step, you got the solute that each of the individual particles in the solute are attracting one another. So you got to break those bonds between the two. Now, these are not covalent bonds. They might be ionic bonds, but they're not covalent bonds. You want to break the intermolecular attractions that hold those molecules together. So this is the solute is solute intermolecular bonds are broken. Okay, this is an endothermic process. That means you have to add energy. You've got to add energy to this solute to break those bonds. Okay, second step has to do with the solvent. The intermolecular bonds holding the solute molecules together, bonds, have to be broken. This is also an endothermic process. You got to add energy to pull those solvent molecules apart so that you got a place for your solute to go. That's why sometimes they call it make a hole. Or actually make lots of holes. Make holes so that your solute will have some place to go. And then the third step is solute solvent bonds form. So when they get together, after you pull them apart, and they get together and form these associations, this is an exothermic process. It's lower energy now. This is increasing the energy, increasing the energy. Now we're going to decrease the energy in an exothermic process. Right? Those 3 steps occur, as we understand it, for every formation of a solution. Now, what affects the rate of the formation of a solution? We know that if you want to make hummingbird juice, you take sugar and water and you just put them together, right? Usually one cup of sugar and 1 cup of water. But if you don't want to wait around forever for it to dissolve, you heat the water up and then you add your sugar. Goes into solution faster. And then you let it cool down before you serve it to the birds because you don't want to burn their little tongues. So what are the things that will increase the rate of solubility, make things happen faster? Well, it depends on the nature of the solvent in the solute, of course. as to which ones are most important. But if you're going to dissolve a solid in a liquid, particle size is one major factor. The smaller the particle size, the more surface area you have to interact with the solvent, and it goes into solution faster. So if you take a big chunk of rock salt and put it in a beaker of water, it may sit there for a month before it finally all goes into solution. But if you grind it up into a fine powder, then you can put it into solution in just a few minutes. Also, the degree of agitation, right? If you want something to go into solution, you generally want to stir it. What agitation does is, think of it this way. If we have our solvent here, and we put our solid in, I'm going to draw it as a cube. That's what it would be if it were sodium chloride. Draw it as a cube. If you just let it sit there, I probably should have drawn it on the bottom. Just let it sit on the bottom. Let that cube sit on the bottom, then the water is attacking the cube, and salt of this substance, let's call it table salt for ease of discussion. Then sodium ions and chloride ions are going to leave the cube and go into solution, but they're going to build up a concentration around the cube, right? Which obstructs more water from coming in and removing more ions. Right? So there's what we call a concentration gradient of sodium and chloride ions around the cube that obstructs more solution. So it takes longer. They diffuse into the body of the solvent if you don't stir it. If you stir it, then you're constantly moving those ions away from the cube and allowing more water molecules to get at it. That will dissolve it faster. Temperature. In most cases, increasing the temperature will dissolve the substance quicker. Now, that won't work for gases because we know that gases are less soluble with the increasing temperature. And some solids are less soluble as the temperature increases. So in those cases, decrease the temperature and they'll go into solution faster. Then the last one is called the common ion effect. What we mean by that is, for ionic solids that we want to put in solution, such as sodium chloride, if the solution already has some ions in it, and we put solid sodium chloride, for instance, in here, we want to get it into solution. It's going to dissolve slower if there are some ions common to the solid already in solution. It slows the process. That's all that means. If there are ions that are common to both in the solution, then it slows the process. Okay. We're going to talk about solubility rules here, but there are rules for solubility of ionic solids in aqueous solution. And I gave you a copy. This looks like this. In fact, it's on a slide coming up, but I gave you a copy like this last week. And this shows you, this allows you to predict the solubility of a cation with an anion if you're going to conduct a reaction involving those two ions, then you can see if the product is soluble or not soluble. But there are some general rules that we can follow. If the first rule is like dissolves like. Have you ever heard that one before? No. What this means is if we say like dissolves like, what we're referring to is polarity. If the solvent and solute are both polar, they're more likely to dissolve, the solute in the solvent. Or if they're nonpolar, they will be more likely to dissolve. So as the difference in polarity gets wider, the probability of dissolving the solute in the solvent decreases. So if you have a polar solute and a nonpolar solvent, you're not likely to get a solution formed from those two combinations. Now, this is a black and white rule, but there's gray area in between. That's why I say the difference in polarity determines whether it's slightly soluble, partially soluble, or completely soluble. Another property. Let's see. This slide is only concerning, yeah. Okay, so that whole slide is on this topic. Thought we were going to have some more. Well, and then there are solubility rules that are taken into account when this chart was built, and the rules are at the bottom. But since you guys are not going to be chemistry majors, I'm not going to make you memorize those rules. If you do enough of these problems, then some of the rules are just they will kind of absorb into your brain anyway. But if you know that you've got, let's say, I don't know, nickel 2+ ion in solution, and you also have phosphate in solution. You follow those down, you follow the cations from the top, the anions from the left, it meets at a grayed out box. That means that nickel 2 phosphate is insoluble in aqueous solution. So this table, it uses those rules, and I'm not going to spend a lot of time on it because you will have the chart available to determine solubility. And there are the rules. If you ever want to use the rules, then they're set up so that if you have a situation where you're applying one rule and then another rule also applies, the one above is the one that takes precedence. So for instance, if you have a compound with sodium and you also have a compound with, let's say, something that says it's insoluble, sulfides, right here. Sulfides are insoluble. But if it's a sodium sulfide, the rule number 1 takes precedence. Sodium sulfide is soluble, right? And you can see that from the chart. You follow across here and find sodium. Actually, all sodium salts are soluble, right? You follow that sodium all the way down, they're all clear. Every sodium salt is soluble. Okay. And there's another example of your chart. So if you have a situation where you know you have a certain cation in solution and an anion as a consequence of perhaps adding two solutions together, then, and those ions are now able to interact, then you can determine if they're going to be soluble. You just find the cation across the top and the anion on the left and follow them down to where they meet. And if they're grayed out, then they're not soluble. We'll talk some more about that as we go. So if the difference in solute and solvent polarity is great, then they're less soluble. All right, here's an example. We get to use our chart. So, do you have copies of everything? Because it's all right up here. If you think you need a copy. Okay. Because I'm going to use this chart right now. And we have today's lab copy there, and next week's lab is also there, in addition to the lecture materials. But if you've already got a copy, then just take what you need. Okay, so which of the following ions in this A through E are generally soluble if they're combined with lead 2+? Okay, so how about sulfide? Right. If we combine it with sulfide, we just look at our table, right? We find lead 2+, which is way over here on the right-hand side, and we follow it down until it meets the sulfides, which is right here. Follow that across, and it's grayed out. So this one would form a solid with that cation. How about this one? Chloride, lead 2+ and chloride. All right, we look down there, chloride, lead 2+. It's also insoluble, forms a solid. How about nitrate? All right, follow that one down, and we find that it's soluble. In fact, all nitrates are soluble. That's one of the rules. So this one will remain in solution. All right, so that one's soluble. How about sulfate? Oh, 2-, sorry. I was thinking phosphate. Sulfate. There we go. So we look at that. Let's see, and follow it down until we find sulfate, and it's insoluble. That's a solid. Okay. So the nitrate combination is the only one that's soluble. And we threw that last one in just to see if you're thinking. You don't form compounds from two cations. Sodium plus and Pb2 plus, they don't form a compound. Okay. So this is the only one, the nitrate is the only one that's soluble out of that group. Okay. Now, when you form a solution, assuming your compound goes into solution, we want a way to express the concentration, because since this is a mixture, then the composition can change. We can have a lot of solute or only a little bit of solute. But instead of just saying it's concentrated or dilute, that doesn't help us much. If we're interested in quantitative determinations, we need a way to express the concentration. And there are several methods. The two that we're going to talk about here, actually there are three that we're going to talk about here. One is percent concentration. The other is molarity, and the last one is molality. All right, so let's get those together. The problem with percent is the same problem I've expressed over and over again. That is a dimensionless number, dimensionless unit. You can't tell whether it's mass of solute per mass of solution, or is it mass of solute per volume of solution, or is it volume of solute per volume of solution? Right? If you purchase alcohol, it will have a percent, a value percent here, something. Let's say it's wine. maybe it's 15%. It'll say ABV. That means alcohol by volume. And that specifies that it's this one right here. Okay. So percent is only valuable if you have determined and you express it as mass, volume, or volume. So usually if you have a solution, then you will say so many percent mass, like that. And that way, anybody that sees your number will know what the expression means. All right. So if it's, so to determine percent by mass, you just need the mass of the solute. Okay. And the mass of the solution. Times 100. And that'll give you percent. We'll look at some examples here in a minute, and that'll become clearer, the use of it. In fact, we're going to do one right now. Okay, calculate the percent by mass if you have put glucose as the solute in a solution of water. Put it in water, you have 5.5 grams of glucose. Okay, and you're going to put it in 78.2 grams of water. Now that's not the total mass of the solution. The mass of the solution also has the solute in it. So you need 5.5 grams here times 100. Okay, that's how you would set it up, and then the rest is number crunching. And it should be 6.6%. All right. Percent by volume, we're going to skip this one and go to this one. Percent by volume is the volume of the solute. That's wrong. It's not the volume of the solvent, it's the volume of the solution. That needs to be corrected. Let me make a note. Okay. That's volume of solute divided by volume of solution times 100. So in this case, 30 milliliters of methyl alcohol, methanol, I abbreviate it this way, methanol. You would write the formula like this. And then enough water to give 435 milliliters of solution. So that's that many milliliters of methanol in 435 milliliters of solution times 100. And that's 6.9%. Now this alcohol by volume is not drinkable. Methanol, wood alcohol, that's the one that you drink and you go blind. That's not ethanol. So if you see this methanol as the alcohol component, then don't drink it. The other thing to recognize is that when we put this methanol in aqueous solution, the final volume is not the volume of the methanol plus the volume of water into which you added it, because that final volume will not be It's not summation. It's not additive. It could be less. It could be more volume. It's usually less. So it could have been 395. Excuse me. It could have been 430 milliliters of water, and 30 milliliters of alcohol gives you a final solution of 435. So it's not additive. That's why they tell us it gives you 435 milliliters of solution. Now, if it's mass, of course, no problem, because the mass is not going to change, but the volume will change. Oh, mass volume. Okay, now we get to look at the second one. All right. So the mass, the percent mass volume is equal to the mass of the solute. That's simple enough. Solute. Okay. And this is usually in grams, and this one is volume of the solution. In milliliters times 100. Now, why would they choose grams for this and milliliters for that? The reason, I think, is because of the density of water. Right? Density of water is very close to 1 gram per milliliter. So grams per milliliter is consistent with aqueous expressions. And then times 100 makes it a percent. 100 milliliters of water should be 100 grams, or very close to it. So, oh, we're not going to get an example? All right. I'm not going to beat that horse anymore. Let's move on. A solution having a mass percent concentration of 10%. Mass percent of 10%. So 10% mass. What does that mean? Well, you definitely have 10 grams of solute per 100 grams of solution. Right? Parts per 100, 10 parts per 100 parts. But that means that the solvent is 90 grams. Because the total is 100. So A would be the correct answer to that problem. How many grams of sodium chloride are needed to prepare 150 milliliters of 0.9% mass volume sodium chloride? Okay, now we have a different expression. We're looking at 0.9%, 0.9% mass volume sodium chloride. Okay, we want 150 milliliters of solution. Okay, and we want it to be equal to, let's see, times 100 equals 0.9. Okay, so we're solving for this value up here. All right, so this one, this would be 100x over 150 equals 0.9. So 150 times that would be 100x equals 0.9 times 150. And then x would be that expression divided by 100. Right, so 1.5 times 0.9. That'd be 1.35 grams. of sodium chloride. There you go. Now, why did they pick that example? Because 0.9% mass volume sodium chloride is isotonic. Sounds like a heartbeat. Ooh.
I take your dumb.
Okay. 0.9% is isotonic with body fluids. That's why they picked that example. All right. Molarity. Okay. Actually, the next expression for concentration is much, much more useful. Molarity. And it's represented by a capital M. And what it means is the number of moles of the solute per liter of solution. Nice thing about this is once you've prepared a solution of a given molarity concentration, it doesn't matter what the solution's made of. Sodium chloride, 1 molar, is the same as 1 molar calcium chloride. So that's convenient. And then since it's expressed in these terms, if you have a certain volume of this solution, it's easy enough to determine how many moles of solute you possess. But since it has volume in the calculation, it is susceptible to temperature changes. Okay, moles of solute per liter of solution. So if we have 1 mole of sugar and 125 milliliters of solution, let's see, is that 2 zeros? So this is 1 mole. How many liters is 125 milliliters? Milli means what? 10 to the minus 3. So we take that and move 1, 2, 3. 0.125 liters. Divide that into 1, and you get 8 molar. So this solution is 8 molar. That would be considered a concentrated solution, not dilute, that's concentrated. Okay, let's work the problem backwards. So if we have 10 molar sugar solution, and what volume of this solution do you need to have 2 moles of sugar? So we got 2 moles up here, the denominator, and then the volume is our unknown. Okay, so we just solve for V. So V, put V over here and 10 over there, would be 2 divided by 10 equals 0.2, correct? Liters. Do they want it in milliliters or just liters? Yeah, 0.2 liters. Okay. So it's like any other formula. Right? If you, in this case, if you have two of the terms, you can solve for the third one. How about these two separate solutions of sodium hydroxide and potassium chloride? All right, so let's set it up. So first one is sodium hydroxide, 100 grams. And potassium chloride, 100 grams. Okay, and we're going to make separate solutions of these two compounds. They're both soluble in water, and we want the final solution to be 250 milliliters. And what's the molarity? Well, notice we don't have moles, we have grams. So we got to convert. Right, there you go. Grams and moles in a quotient. We need the molar mass of sodium hydroxide. So sodium is 23 rounded off. 23 for sodium. Oxygen 16. Hydrogen is 1.01. So that's, let's see, 10, 3, 4, 40.01. 40.01 into 100. Is 2.4994 moles of sodium hydroxide. Okay, now let's see how many moles do we have of this one. Potassium chloride. Potassium's 39.10. And chlorine is 35.45. So we got 5, 5, 14, 7, 74.55. There we go. So 100 divided by that. 74.55 is 1.3414 moles of potassium chloride. Now we can put those, we can follow our formula. Molarity equals the moles, 2.4994 divided by liters, 250 milliliters. So that's 0.25 liters, moles per liter. So 2.4, let's see, let me swap that one and divide it by 0.25. 9.9975. Let's see, we're going to round it off to 4 places. 1, 2, 3, 4. 9.998 molar. And this one is 1.3414 moles per the same volume. Okay, so let's swap that one and divide it by 0.25. 5.365, 5.366 molar. So the point of this one is, this exercise is that you may have the same masses, but you have different moles. So that gives you, even with the same volume, it gives you a different concentration. Sodium hydroxide has a higher molar concentration, molarity, because it's a smaller molecule. And let's see if they agree with me. They're rounding it off to 10. 5.37. Okay. Okay. So now that we have, we know how to express molarity concentrations, there's a practical problem that has to be overcome. In a former life, I was active in soil testing, which means you have certain solutions that you prepare, most of them salt solutions, some of them acidic, some of them basic too. But a certain concentration, and you put a certain volume of that extractant in a certain mass of soil, and you mix it up and let it sit and filter it, and you take the solution out and analyze it. Well, our soil testing lab would do hundreds of these extractions every day. And to make up a fresh solution would take an hour or more in the morning, because you have to wait for everything to go into solution and then you add them together and so forth. It takes too much time. So what we would do is make up a stock solution at a higher concentration and keep it in a big jug like that one right there. And then when we needed a working solution, we'd take the concentrated one and dilute it down to the concentration that we needed. And that would just take a couple of minutes. So why does that work? Why does this dilution process work? Well, let's say you have your jug. You have your jug here with a spout on it, and you have a solution in here, and it's at a concentration. I'm going to use molarity. That's the concentrated molarity of this solution. But we want, say we have a volumetric flask here that's marked off, say, 1 liter volume. We want to dilute some of this with more solvent and give us a more diluted concentration, say molarity of the diluted concentration. Okay, so we take a volume out of here, volume of the concentrated solution, and we put it in here. And the volume of the diluted solution is 1 liter. Okay? Now, these two values are different. These two values are different. What do they both have in common? When you take this volume out of here, look at this. Molarity equals moles per unit volume. So when we take a volume out times molarity, we have a certain number of moles from the concentrated side, right? Molarity times volume equals moles. So we've taken out a certain number of moles of the solute, and we put it in here, right? So on the way, did that number change? No, it's the same value. So this is also equal to the moles on the diluted side. Well, what does that equal to? That's equal to, let's see, this is concentrated. That's equal to molarity of the dilute times the volume of the dilute. Okay, so if A is equal to B and B is equal to C, then A is equal to C. So if this one's equal to that one, then that one's equal to this one, and these two are equal, that means this is equal to that. So the concentrated expression is equal to the diluted expression. And that's how we do dilutions. So you can, one of these will be unknown and you can solve for it. Sometimes you'll see the expression M1V1 equals M2V2. 6 of one, half a dozen of the other. Okay. So let's take an example. How would you prepare 100 milliliters of 0.9% saline solution in water from a 10% saline solution? All right, if they're going to be the same percent expressions, which would be mass per unit volume, then notice that molarity is the same on both sides, volume is the same on both sides. This could also work with any other form of expression for concentration. That's what we're doing here. So what's the concentrated concentration is 10%. Okay. The diluted is 0.9%. So the volume of the concentrated and the volume of the dilute are other two terms. 100 milliliters of this final one, 100 milliliters. And this is our unknown. So I like to do it like this, so I get things in the right position. So when I plug them in the formula, I don't put them in the wrong place. So concentrated would be 10 here. Volume of the concentrated is unknown. Diluted concentration is 0.9. And these are both percent, right? And this one is in milliliters. So if we solve for this one, it's just 0.9 times 10, which is 90, right? Divided by 10, which is 9. So 9 milliliters of the concentrated one diluted to 100 milliliters. Okay, there we go. 9 milliliters of stock diluted to a final volume of 100 milliliters, which means, well, roughly 9 milliliters plus 91 milliliters of water, which is, that's not exact. What you need is a 100 milliliter volumetric flask so that the final volume can be determined. Because just adding 91 milliliters to this may not give you the right volume. Yeah, there you go. It's better to do it to a known volume rather than adding a certain volume. Now, if you're only ballparking it, that's okay. But if you want to be accurate, use volumetric glassware. All right. Let's see how we're doing on time. I got 24 minutes. Then we need to get to the lab. Let's see, let's do that. All right. A 0.5 molar solution of sodium chloride sits on a lab bench. Which of the following would decrease the concentration of the salt? Decrease. Add water to the solution. Yeah, that would decrease the concentration because you're increasing the solvent. So A, yes, A would work. Pour some of the solution down the drain. No, because you're pouring the solute and solvent at the same time. Add more sodium chloride. That would increase the concentration. Let the solution sit out on the open air for a couple of days. That would evaporate the solvent and increase the concentration. And at least two of the, no, just the one, A, works. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide? So in this case, we've got concentrated molar volume, concentrated, dilute, and dilute. So the molarity of the concentrated one is 2 molar. Minimum volume of this diluted to that. So this is the unknown. And we're going for 0.8 molar. And we want a final volume of 150 milliliters. The nice thing about this formula is that you can use any units of volume you want, because whatever you use on one side is going to be the volume units for the other when you answer it, because it's a ratio. So we don't have to change it in this form. We don't have to change the volume to liters. It's only when we have that, the simple calculation with this formula, that has to be liters. But in this ratio form, we can just plug these values in, right? 2 molar times volume and 0.8 molar times volume. Right? And solve for the volume. 60 milliliters should do it. All righty. Okay. Here's the suspension that looks like a solution. It's called a colloid. A colloid is not a solution, it's a dispersion. So instead of the solute, we have a dispersed phase. And instead of a solvent, we have a dispersing medium. So those are the analogous terms. We can't call it solute solvent because it's not a solution. And it's based upon particle size. Small, very, very small particles in a dispersing medium, right? These little tiny particles are being slammed on all sides by and transferred kinetic energy from the dispersing medium. So if they're small enough, then you can hit them hard enough to where they won't settle. They'll just stay suspended. That's a colloid. Let's see, examples of a colloid. You like Jell-O? Jell-O is a colloid. There are other types that are not so desirable, like smog. Smog is a colloid of smoke and fog together in the atmosphere. Okay, so how do we tell the difference? Well, there's a procedure. Easy way to tell the difference. It's called the Tyndall effect. So if this is a solution, and we have a flashlight over here, and we shine a beam in there, and it comes out the other side. So we've got our eyeball over here, and we can see it, right? We can see the beam coming out. You can do that with a colloid or a solution, either way. But if you turn right angles and you look around on this side, your eye, if it's a colloid, you will be able to see the beam in that medium. If it's a solution, you won't. That's all it is. That's the Tyndall effect. Because the particles in a colloid are not dissolved. They're not in the holes. They're separate particles, and they will disperse a light beam passing through them. The next slide should show you an example. The first one, the yellow one, is a solution. You can't see the beam. The second one is a colloid, and you can definitely see the beam there. That's the Tyndall effect. In fact, in my general chemistry class, we do a titration with, have we done one of those with a burette? I don't think we have. Anyway, we're looking for the endpoint when a certain change occurs, and the change is the formation of silver chloride. Silver chloride is very finely divided. It's difficult to see. In fact, it forms a colloid in the solution as you add your reactants. And finding the endpoint is critical. But if you wait till you can see it with ambient light, then you've gone way past the endpoint. So we use the Tyndall effect. We dim the lights, and as we're adding solution, we can see the silver chloride form and then disappear as we stir it. But if we get to the point where we stir it and we see the beam and it doesn't go away, that's our endpoint. We use the Tyndall effect in that experiment. Okay. So when we've got this, a suspension is one in which the dispersed phase particle size is too large to stay suspended. It can't form a colloid. So a suspension will eventually settle out. Some of them may take a long time. Some of them may happen really quick. Like when we were separating salt and sand in a previous experiment, right? Binary mixture. We stirred that stuff up in water, and you notice pretty quick that the sand just went, dropped right out. That's a suspension. Okay, this slide in really fine print compares solutions, colloids, and suspensions. Suspensions are always heterogeneous. Colloids, however, are homogeneous, and that presents a problem because we've said earlier that homogeneous mixtures are solutions. But there's one exception. If it's a colloid, it may be homogeneous, but it's not a solution. Solutions, as the solutes, can be atoms, ions, small molecules. In fact, some big molecules can go into solution. They're transparent to light. The Tyndall effect does not show dispersion. Particles don't settle, and you can't filter the particles out. There's no way. But a colloid, while it's homogeneous, these particles are, I should say, never ions. They're small particles or individual molecules. You can detect their presence with the Tyndall effect, right? They're not transparent. But the particles don't settle. Right? So colloid is kind of in between a solution and a suspension based on particle size. And you can't filter the particles out of a colloid. They're too small. Suspension is heterogeneous, much larger particles. It's not transparent, obviously. And the particles will settle over time in a gravitational field. In fact, sometimes if you want them to settle really fast and it's taking too long, you stick them in a centrifuge and just artificially increase the force of gravity, right? Centrifugal force. And you can get them to settle quicker. But the particles can be filtered. Now, sometimes it takes a very, very fine pored filter to do it. And it takes a vacuum to suck it through, but they can be filtered. Okay, that's a colloidal dispersion. All of those apply. Now let's talk about colligative properties. What's a colligative property? Colligative properties are those that are associated with solutions, and the physical property that's defined varies only with the number of solute particles. In other words, the number of moles of solute determine the magnitude of the property. So that's good. We use that to good effect because it doesn't matter what the particles are, right? If it's an unknown compound, then you can use a colligative property to determine how many moles there are of that compound. And then if you have measured its mass before you put it in solution, and then you use a colligative property to determine the number of moles, you can calculate the molar mass of that compound without even knowing what the compound is. Next week, we're going to do one of those. We're going to use a colligative property, freezing point depression. Okay, so these are the most commonly used colligative properties. Vapor pressure. Vapor pressure changes with the number of particles dissolved in a solvent. We can elevate the boiling point by adding a solute to a solvent. That's why the fluid in your radiator has ethylene glycol in it. It's not just water, because the engine gets hot. Its temperature rises in your engine above the boiling point of water. Right. So if you just put plain pure water in there, pretty soon it'll all be boiled out, and your engine run dry and it seizes up. So we put ethylene glycol in there at a very high concentration, and that increases the boiling point so that you can run your engine at 150 centigrade or 200 or 250 centigrade, and it won't boil out. Nice thing also is that in the winter, that ethylene glycol also depresses the freezing point of water. So it won't freeze at 0 degrees. If the temperature outside goes down to minus 15 Fahrenheit, which is a lot lower centigrade, then the water won't freeze in your engine block. What happens when water freezes? It expands. So if you just have water in your engine block and it freezes overnight, it could crack the block. Or most engines are fitted with poppets on the side of the block. So if it does happen to freeze, that poppet will blow out instead of cracking your block. And then you just have to thaw it out, drain it out, and go to the dealer and have another poppet shoved in that hole, and then don't do it again. And the last one is osmotic pressure. So what is osmotic pressure? Everybody's heard of osmosis, right? If you've had a biology course or anatomy and physiology, you know about osmosis. Isotonic solutions, hypertonic, hypotonic solutions. It's the movement of water across a semi-permeable membrane based upon a difference in concentrations of the solutes on either side of the membrane. And it builds up a pressure depending on that difference in concentrations. We're going to quantify it in just a minute. Okay, vapor pressure change. This is Rayleigh law. So vapor pressure is above the solution. Not of the solution, above the solution, in the headspace above the solution. The vapor pressure is equal to the pressure of the pure solvent times a factor. And this factor is what does X mean? X is the mole fraction. In this case, the mole fraction of the solvent. Mole fraction of the solvent. That was starting to give out on me. Pick another one. About this one. So what's the mole fraction? Well, if you have a solution and you know in here you have, say, I don't know, 25 moles of solvent. And you put, say, let's try to make it easier. Yeah, 2 moles. You put in here 2 moles of solute. So what's the mole fraction? Well, it is a fraction. It's a decimal fraction relating this one to the total. So it'd be 2 divided by 27 would be the mole fraction of the solute. And whatever that happens to be, I painted myself into another corner. 0.074. And this one would be 25 over 27 would be the mole fraction of the solvent. So that'd be 25 divided by 27. 926. 926. Notice that if you only have one solvent well, you always have one solvent. You only have one solute, that the summation of the mole fraction is 1. If you have more than one solute, right, then they would be added together and you get 1. It's always that way. So here we want the mole fraction of the solvent. That would be 0.926 in this example. And if we knew the vapor pressure of the pure solvent at a given temperature, then we multiply the mole fraction, and that would give us the vapor pressure of the solution. Okay? That can't be any simpler than that. So that's the first colligative property. I hope that color is getting picked up okay on the board. I mean, on the recording. Let me switch to black. Okay, the second one was, what did we say the second one was? Oh, okay, we're going to try to explain why that vapor pressure decreases. Rayleigh law, which is this, works because in the pure solvent, you've got nothing but solvent molecules at the surface. And they're migrating into the vapor phase, and then they're returning from the vapor phase, and you get this is play back and forth. Same rate of evaporation and condensation occur at the same rate. And in a closed vessel, eventually you build up a pressure. Well, if you put a non-volatile solute in there, and it doesn't participate in this vaporization process, then what it does is two things. It occupies space at the surface, right? You got these yellow molecules in our example, and those are places where you can't fit solvent molecules to be vaporized. So you don't get as many in the vapor phase, and that decreases the pressure. But also there might be interactions between the solvent and the solute that are holding the solvent molecules back. So you get those two processes that are decreasing the pressure. All right, boiling point elevation. So that is expressed as a change in temperature. So if we know the boiling point of the pure solvent, then we add some solute, it increases the boiling point. Okay, that's the change in temperature. That's not the boiling point, that's the change from the boiling point. So if we had water and we increase the boiling point by some process, then the change would be 5 degrees C. Okay, it's a change in temperature. And we're only interested in the absolute. All right, so if the process gives you a negative number, which it won't in this case, but we would say absolute value, just put 2 bars on each side. We only want the change, absolute value of the change. Okay, that's equal to a factor, the boiling point elevation constant, which is characteristic of the solvent. Every solvent has a different value here. And then the other factor is the concentration of the solute. Now, that's not molarity. Okay, that's molality. Okay, it's similar to molarity, except it's equal to moles of the solute divided by the kilograms of the solvent. Okay. Now, why would we use that instead of molarity? Well, because we're interested in temperature change. And what happens to molarity if the temperature does change? The molarity changes because it's based on volume. So we have to use molality. All right. For water, this value is 0.51 degrees C per molal. All right. Let's see, standard temperature and pressure. 25 degrees Celsius is standard temperature for everything except for the gas laws. The gas laws are 0. Don't ask me why. 1 atmosphere is standard pressure for all solutions, and 1 molar is standard concentration. If that is part of the problem, if it tells you blah, 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 standard temperature and pressure, that's what they mean. 1 atmosphere pressure and 25 degrees C temperature. The third one is similar to that one. All right, this is boiling point elevation. This is freezing point depression. So the freezing point is going to drop as we add solute. Right? That's how we make ice cream. And we take ice and just shower it with rock salt. And it makes the temperature of that solution drop. We've decreased the freezing point. So it decreases the freezing point, in fact, below what's necessary to freeze custard. That's my favorite. Okay, so we have a K, a freezing point depression constant for the solvent, which is different for everything. In this case, we're told that for water, it's 1.86 degrees C per molal, and then the molality of the solute. Okay, this is the one we're going to use next week. So if we add a non-volatile solute, we decrease the vapor pressure. And the last one is osmotic pressure. This needs some explaining, but the symbol we use for osmotic pressure is the same one as pi, and pi r squared. We use pi for osmotic pressure. Okay, there's a difference between semi-permeable membrane and selectively permeable membrane. A semi-permeable membrane only allows the passage of water and molecules that are smaller than water, especially gas molecules like oxygen, nitrogen, helium, whatever the case may be, will pass through a semi-permeable membrane. We're only interested in the passage of water. Whereas a selectively permeable membrane is constructed in such a way that the pore sizes are standardized. They're regular pore sizes depending on the choice of the selectively permeable membrane. You can get them very small or larger, and they will allow certain size molecules to pass. That's selectively permeable membrane. Now, what happens when, in this case, when we have a semi-permeable membrane, and for our argument's sake, this only passes water in our example, and we have a dilute solution of, say, salt in this outer beaker, and there's your membrane on the tip of it, and we have inside is a concentrated solution of salt. And initially they start out at the same level. It's kind of hard to tell there, but let's assume that they're at the same level. All right. So which way is the water going to move? The water always moves through a membrane from an area of high water concentration to low water concentration. So what does that mean in terms of solute? That means water moves from low concentration solute through the membrane to high concentration solute. So the water here is moving through the membrane into the tube. And it will continue to do that until there is sufficient pressure as it rises in the tube, there's sufficient gravitational force, pressure, to oppose the movement of water into the tube. So you get those opposing forces. In fact, they're rates of movement. The rate of movement of water from the tube into the solution, outer solution, is the same as the rate of water moving in. It's a dynamic process. Well, so the osmotic pressure is a difference between the level of the solution outside and the level of the solution inside. If this is an aqueous solution, that would be like so many millimeters of water. But typically, this expression, which should be on the next page. Wait a minute. They didn't give the formula. Okay. Oh, I messed up. The formula for osmotic pressure is equal to, in this case, we can use molarity because the volume is not an issue for osmotic pressure. So we use molarity times the gas constant times temperature. And temperature would have to be in Kelvin because the gas constant has Kelvin in it. So let's see if our units work out. So this is moles per liter. This is liter atmospheres per mole K, that's R, and temperature would be in K. So let's see, K cancels, mole cancels, liter cancels, and leaves us with atmospheres. So that's right. Osmotic pressure is equal to molarity times the gas constant, when this is the 0.08206, and temperature in Kelvin. And that will give you a value of osmotic pressure in atmospheres. Okay, this is trying to explain why the semi-permeable membrane works the way it does. On the left, you see, let's say we have pure water on this side. And we have a solution on this side with whatever solute molecule cannot pass through the membrane. So the processes are such that the water molecules can move through the membrane, but there's more water molecule on one side than there is on the other because the solute molecules are in the way. So the speed of the movement of water molecules from the pure side is higher than it is from the other side with the solution. And that keeps going until you get a balance of pressure. So eventually you get enough pressure up here as the level rises. You get enough pressure up here so that you can balance the rates. And in fact, we use in the laboratory where I used to work, and then there are some cities that actually use a process called reverse osmosis to produce drinkable water from salt water. So all you have to do is artificially increase the pressure on the saltwater side of the membrane so that it drives water molecules. You increase past the osmotic pressure of the salt solution, and you drive water molecules back through the membrane and produce drinkable water. And then what's left on the other side is a concentrated brine, and you just slough that off. Okay. So by definition, the osmotic pressure is the pressure required on the concentrated solute side that will stop the movement of water through the membrane. It will be static now. It doesn't go all the way to the other side. It doesn't go one side or the other. It just stops it. This is an interesting problem I wanted to work out. Let me see. I'm past time, so is this close to the last slide? We got a little bit to go. This lab doesn't take very long, and there's only one of us. I'll be your lab partner. And I'll build a table on the board, and we'll put data from the experiment on the board so it's recorded and the rest of the class can see it. I'm going to go through this one really fast. A long time ago, when I was a kid, I wondered, when I started to learn about the physics of the natural world, I knew that if you pull a vacuum, you stick a tube into a bucket of water and you pull a vacuum on the top, you could get the water to rise in it. But you could only go so high, right? If you have a vacuum above the water, then it's being pushed up by the atmosphere, and it can only go so high before it stops. And in fact, if you pull a vacuum, it can only go up to 33 feet. And that's as high as it'll go, no higher. Well, that begs the question, if you're interested in knowing how water gets to the top of a sequoia tree, which is 250 or 300 feet high, how does it get up there? Well, the first proposal was there's a column of water inside the tree's xylem tissue, and it's a continuous stream all the way to the top. And if you evaporate water from its leaves, then that sets up a suction and it pulls the water up. Well, subsequent to that, experiments were conducted and found that that couldn't happen. I don't have time to go into the experiments, but another proposal is more believable. And that has to do with, rather than sucking the water up in the tree, we push it from the bottom. So what kind of forces could drive water to 300 feet up a sequoia's tree trunk? Well, as a matter of fact, it's osmotic pressure. The osmotic pressure in the roots of the tree, right? Each of the cells in the tree roots has a semi-permeable membrane around it, and there is concentration of solutes in the cells sufficient so that you build up an osmotic pressure of 20 atmospheres, right? 20 atmospheres. It could be higher than that, actually. So can 20 atmosphere pressure, osmotic pressure in the roots of these trees, drive the water, push the water high enough to reach the top? That's the question. So can it go 300 feet high based on that pressure? Well, we need to convert to millimeters first. So let's take 300 feet and convert it to millimeters. That's how tall the tree is in millimeters. Why do we do that? Because we're going to change 20 atmospheres to millimeters of water, right? 20 atmospheres can be changed to so many millimeters of mercury, right, in a barometer that we studied last time. But we're using water. No, we're not using mercury. So we have to incorporate the specific gravity, the difference between density of water and mercury, which is 13.56. So once we do that, we find out that 20 atmospheres will support a column of water that's 2 times 10 to the 5th millimeters high. Well, the tree is only 9 times 10 to the 4th. Yeah, there's enough pressure, osmotic pressure in the roots of a tree to drive the water to the top. Okay, I thought that was neat. And a simple calculation. So there's another term, osmolarity. Osmolarity takes into account any dissociations of the molecules that go into solution. So if we have a molarity of sodium chloride equal to, say, 1 molar, the osmolarity, once this goes into solution, it produces sodium ions and chloride ions. So it's twice as many particles as the whole. So that means you double. So osmolarity, and this doesn't have an abbreviation. Osmolarity equals molarity, in this case, times 2. That's what this is, the little I. That's the Van't Hoff correction factor. And basically all you need to know is, how does this break apart? If it's calcium chloride, CaCl2, the correction factor I would be 3, because you're producing 3 ions for every 1 molecule. Okay. If it doesn't dissociate, then the osmolarity equals the molarity. So for table sugar, I would be 1. Right? So there we go. 3 molar sodium chloride is 6 osmol concentration. All right. Now, for some of you, this will be a review. If you've already had biology or anatomy and physiology, a hypotonic solution is one that has a lower osmotic pressure than is within the cell. So the concentration of the solute outside the cell is lower than it is inside the cell. Now, if that's the case, which way is water going to move? The water concentration of a hypotonic solution is higher outside the cell. So the water would move into the cell. Hypotonic solutions cause cells to swell. Okay, hypertonic solutions, just the opposite. The concentration outside the cell is higher for the solute, which makes it lower for the water, and water then migrates out of the cell into the surrounding solution. And isotonic is perfectly balanced. So water's not going to move either direction. That's the kind of solution you want to give your patients. If you set up an IV drip, you want the solution to be isotonic to their tissues. Otherwise, you could kill them. Right? We don't want that. Okay, so on the left, a hypotonic solution would cause hemolysis of blood cells. In other words, they swell until they rupture. And a hypertonic solution causes them to crenate. That is, they lose water to their surrounding solution and they shrink and get bumpy. Okay. Now, 0.9% sodium chloride is roughly isotonic. That's as close as we can get. Emergency medical techs have this solution that they use on non-diabetic patients. If you have a diabetic patient, you can't use a sugar solution, right? You can send them in a shock. But if they're not diabetic, then you can use a 5% mass to volume glucose solution. And this is abbreviated D5W. D stands for dextrose. D5W is dextrose, 5% mass volume. That's what D5W means. And if you do the calculations and determine what's the osmol value for that, it's 0.2775. That, in fact, is isotonic to cells. I think 0.9% sodium chloride is a little high, not too high, just a smidge high. But there are other problems with sodium chloride solutions that it's not just isotonic, it's flooding your system with sodium ions and chloride ions. And that overworks your kidneys. because they have to get rid of that stuff. That's why isotonic solutions in hospital settings are usually mixtures of different things. One that I'm familiar with is a Ringer's lactated Ringer's solution. Oh, here it is. 0.9% sodium chloride is 0.308 osmol. So the D5W is 0.275, which is closer to ideal. So 0.9% sodium chloride is a little high. And here's a reference right here that talks about the flooding of your system with sodium and chlorine if you use the 0.9% sodium chloride. So you can go to that site if you want to learn more about it. Okay, isotonic solution is one in which the osmotic pressure equals that within the cell. Osmolarity of a solution is determined by multiplying the molarity of the solution times the number of particles produced per formula unit. So sodium chloride would be 2, calcium chloride would be 3, ammonium phosphate would be 4. All right, so we have run out of time. I'm going to have to skip these concept questions. Let's see, does it work them out? Yeah, we get some worked out here. So we're finding out, what do we need to do? Identify the solute and solvent first, and then do the calculations to find out what the concentration of sodium hydroxide is in this situation. And then this one is interested in the molarity, the percent mass to volume, and the osmolarity of this solution. So you calculate each of those three. Okay. So that's it for chapter 8. And next week, we'll do a review on chapter 7 and 8 based upon that review document that I give you in class or you have available in Brightspace. So I encourage you to work problems in that review document and come to class with any questions that we can hammer out before the exam on the following week. So it's 2 weeks from today is the next exam.